In this lesson, we will derive equations for the hydrostatic pressure distribution. A common assumption for liquids is that they are incompressible. That is, their density and specific gravity do not change significantly throughout the region of interest, and those quantities are assumed to be constant. Here is a tank of static liquid. Points 1 and 2 in the liquid are separated by a distance h. We can obtain an equation for the pressure difference between these 2 points by starting with the hydrostatic pressure gradient dp dz equals negative gamma. Bring dz to the right side of the equation and integrate from point 1 to point 2. On the left side of the equation, we integrate from pressure P1 to pressure P2, and on the right side of the equation, we integrate from height Z1 to height Z2. Since the liquid is assumed to be incompressible, we can pull negative gamma out of the integral on the right side, making that integral much easier to evaluate. After integrating both sides, the equation becomes P2 minus P1 equals negative gamma times Z2 minus Z1. We can find the difference in pressure between the 2 points by simply knowing their difference in elevation and the fluid's specific weight. And it's important to remember that this equation is only valid if the specific weight of the fluid does not change significantly from point 1 to point 2. Gases can be compressed much more easily than liquids, and using the equation we just derived can sometimes lead to significant errors when applied to gases. So we need to derive an equation that accounts for changes in density. We start again with the hydrostatic pressure gradient. For most applications in fluid mechanics, the ideal gas approximation is usually valid for gases. So we replace density with P over RT and separate variables by moving pressure to the left side of the equation and moving dz to the right side of the equation. Then we integrate from point 1 to point 2. Let's bring this equation to the top of the screen and continue working. Both the gravitational acceleration g and the specific gas constant r can be pulled out of the right integral since they are constant. But we would need to know how temperature varies with height in order to solve this integral. If temperature does not vary significantly with height, like in a well-mixed gas, we can assume temperature is constant and pull t out of the integral. Evaluating both integrals, we obtain the natural log of P2 divided by P1 equals negative g divided by RT times Z2 minus Z1. Rewriting this equation, we obtain P2 divided by P1 equals e to the power of negative g times Z2 minus Z1 divided by RT. So we can find the ratio of P2 to P1 if we know the difference in elevation of the 2 points and the temperature of the gas. In the real atmosphere, temperature often varies significantly with altitude. Most engineering problems deal with the lowest layer of the atmosphere, which is called the troposphere. In the troposphere, the temperature decreases by approximately 6.5 Kelvin per kilometer on average. This quantity is called the lapse rate and will be denoted by beta. We can use this relationship to find an equation for how temperature varies with elevation. Take the lapse rate equation and move dz to the right side, then integrate from height z1, where the temperature is T1, to some arbitrary height z, where the temperature is T. Pull negative beta out of the integral because it is constant, and we have T minus T1 equals negative beta times z minus z1. We can solve for T and plug this expression for T into the hydrostatic pressure distribution equation. After some integration and rearranging, we obtain the following equation for the pressure change of a compressible fluid in which the temperature varies linearly with height. It should be noted that the equation used to predict pressure changes in incompressible fluids works reasonably well in the troposphere if the altitude difference is not too great. For example, for a height difference of 1,000 feet, using the incompressible equation produces only a 2% error from the equation shown in red on this screen. It is important to remember that pressure only varies in the vertical direction for static fluids. Here we have two open containers filled with the same liquid that has a specific weight gamma. Both containers are filled to the same level. Now we label some points in the containers. Point 1 is at the same height as point 4, point 2 is at the same height as point 5, and point 3 is at the same height as point 6. The pressure at point 1 and point 4 are equal since they are both exposed to the atmosphere. The difference in pressure between points 1 and 2 is gamma times the vertical distance hb. The same pressure difference exists between points 5 and 4. Since P1 is equal to P4, this means P2 is equal to P5. The difference in pressure between points 1 and 3 is gamma times the vertical distance hb plus ha. There is the same pressure difference between points 6 and 4. Since P1 and P4 are both atmospheric pressure, this means P3 is equal to P6. Now let's examine two additional points, point 7 and point 8. Point 7 is at the same depth as point 3, and point 8 is at the same depth as point 6. Since pressure does not vary in the horizontal direction for static fluids, this means P7 is equal to P3, and P8 is equal to P6. This demonstrates an important characteristic of static fluids. Pressure is only a function of depth from the surface, regardless of container shape. Now let's add a third container and fill it with the same liquid to a depth HA plus HB plus HC. We identify points 9, 10, 11, and 12 in the middle container. The pressure at point 9 is the ambient pressure PA. To find the pressure at point 10, we use the hydrostatic pressure equation for incompressible fluids. P10 minus P9 equals gamma HC. Rearranging the equation and plugging in PA for P9, we obtain P10 is equal to PA plus gamma HC. Notice that although P1, P10, and P4 are at the same elevation, P10 is greater than P1 and P4 because it is at a greater depth from the surface. To find the pressure at point 11, we use the equation P11 minus P9 equals gamma times the quantity Hc plus Hb. Rearranging the equation and plugging in PA for P9, we have P11 is equal to PA plus gamma times the quantity Hc plus Hb. The pressure at point 11 is greater than the pressures at point 2 and point 5, even though all 3 points are at the same elevation. Finally, to find the pressure at point 12, we can use the equation P12 minus P9 equals gamma times Hc plus Hb plus Ha. Rearranging the equation and plugging in PA for P9, we have P12 is equal to PA plus gamma times the quantity Hc plus Hb plus Ha. The pressure at point 12 is greater than the pressure at points 3, 6, 7, and 8, even though all 5 points are at the same elevation. Some fluids are immiscible, that is, they do not mix. Oil and water is a classic example of this behavior. Here we have two static fluids in an open container, liquid A and liquid B, that have different specific weights. Liquid A has a thickness HA and liquid B has a thickness HB. The liquid on the bottom will always have the larger specific weight. We label 3 points. Point 1 is at the interface between the atmosphere and liquid B, point 2 is at the interface between liquids A and B, and point 3 is at the bottom of liquid A. We now find the absolute pressure and gauge pressure at all 3 points. At point 1, the absolute pressure is the ambient pressure, PA, while the gauge pressure is 0. At point 2, we add gamma B times HB to the absolute pressure and gauge pressure. For point 3, we simply add up the pressure contributions from each layer. The absolute pressure is the ambient pressure plus the contribution from the first layer, gamma B HB, plus the contribution from the second layer, gamma A HA. the gauge pressure is gamma B HB plus gamma A HA. The gauge pressure is the absolute pressure minus the ambient pressure. The pressure difference between points 1 and 3 can be determined by adding up the contributions from each layer between them. P3 minus P1 is equal to gamma A HA plus gamma B HB. Notice that the pressure difference is the same whether we use absolute or gauge pressures for P1 and P3.